Hello students, welcome back to our lecture on RTOS. So in the previous class we have discussed about how to create a task and schedule it for a particular delay time. Okay, so in that class we have only created one single task. So today we are going to create two or multiple tasks, and we will run it according to we are going to give a particular time for the CPU to execute these tasks. So it means we will slice the CPU time for each task. So this each task will get CPU time. CPU can execute the task according to the delay function we give. Okay, so going to the keel IDE, let's see how to create a new task and run those two tasks concurrently. So here we have already given created a task using x task create function. So I am going to call that API function again for creating another task with the priority 1. Okay, so here I am just copying the same line below. So x task create, this I am giving LED blinker 1. Okay, I just changed its task name, so that is LED blinker 1, and this is going to be LED blinker 2. So here also we need to change the name. Okay, so this is LED 1, and I'm going to give LED 2 as its descriptive name. So I'm allocating a minimal stack size. This I have already discussed in the previous lecture. What is the amount of minimal stack? Okay, just 90 into this unsigned short. This is the amount of stack size we have allocated for each task. So we are not passing any arguments here, so it's kept as null here. And the priority in the priority argument, this going to be priority 2, and we can give its priority as 1. Okay, so and we are not going to manipulate our task using a task handle variable or pointer. Okay, it's just a pointer. Okay, pointer to the TCP block of the task. Okay, so actually we are not going to use that function in this program. So just created two variables, sorry, two task here, and I didn't to create a I have to create its task function here. So for that, this is the prototype, and I just want to copy paste below. This is LED blinker 1, and this is LED blinker 2. Okay, then I'm going to define the task here below. Okay, just copying. After that, what I'm going to do is we just want to blink two LEDs connected to two different pins. Okay, so this LED is connected to the pin 31. Okay, and this should be at pin 30. So we are going to turn on the LED which is connected to pin number 30. Okay, so I am making pin number 30 as high, and this is also I am clearing the pin 30 using IO0 CLR register. Okay, so by writing 1 to the IO0 CLR at the 30th bit position, we can clear the 30th pin. Okay, we can set the 13th pin to the low. Okay, just giving 30 here. So after that, I'm going to just run the program, and after we can check by debugging. So when we debug the code, okay, we can select the peripheral here. So in peripherals, okay, debugging, okay. So there is an error just encountered in this program. We have forgotten to give the semicolon somewhere in our program. Okay, let's check that. So here we missed the semicolon. That was the error. Okay, now compiling. Just debug the code. Our IDE is in going to debug mode. Okay, and running the program, we can see here two pins are blinking concurrently. But what we can do if we want if we don't want to blink those two pins concurrently. uh, for example, if we want to blink the pin 31 for 5 times or more than 5 times, and only after that we are going to blink the 30th pin. So what we are going to do, just we need to change the delay which is given here. Okay, so we are going to increase the delay of LED blinker 1 here. Okay, so when the delay calls, when this delay line executes, what's really happening is that the task with priority 2, it is the task LED blinker 1. So this task will start to execute at first. Okay, and when the code reaches here in the wait task delay, this task is going into the wait mode. Okay, waiting list. So this task is temporarily suspended. Okay, temporarily suspended. This task is in wait mode because we have given a delay. So during this delay time, this what is really happening is that this CPU will stop executing this task because this task went to waiting list. Okay, so CPU will stop executing the first task, which is LED blinker 1. After that, the CPU will go to execute this task during the delay time of the first function. Okay, when the first function we put into delay, and at that delay time the CPU will give time to execute the second function. Okay, the second task. So this task is going to execute next. Okay, when this task reaches here, okay, this task reaches here, then it is also going to wait. Okay, it's also put into waiting list. So at that time this CPU will go and execute this task when the delay of the task ends. Okay, when this delay ends, this task will again continue to execute. So the CPU will now clear the write 1 to the IO0 ZLR register, leads to the clearing of or setting the IO0 pin 31st to low. Okay, so pin 31 goes to low and LED turns off, and after turning off, the function again calls wait task delay. At that delay time, this CPU again comes to here where it stopped previously. Okay, so from here it again started to execute. So it clears the 31st pin. Okay, and the LED 2 will also turned off, and after that it's also calling again a wait task delay, and during this delay time the CPU will go and execute this LED blinker 1 function where it stopped. Okay, previously where it stopped at a this line with task delay. Okay, this delay is being executed and the task was in the waiting list. So after the delay is over, the task will again start to execute. Okay, until its delay is finished. Okay, this is how this real-time operating system works. Okay, I hope you got an idea about how RTOS works now. So let's check with the other delays. Okay, we can alter the delay in order to check how these functions really work. So here it is 1000 and I'm going to, sorry, here it is 100 and I'm going to make it 1000. Okay, so we find that this LED blinker one will go to waiting mode for this 100 milliseconds, then only it will turn off this LED blinker one, LED one. Okay, and during that 100 milliseconds, what will happen? During that 100 millisecond, this LED blinker 2 will continuously execute because there is no other task to execute. Only LED blinker 2 is existing because the LED blinker 1 already went to the delay waiting list. Okay, it is in it is not active actually. Okay, so let me again compile the code. Okay, and you can see both the okay, sorry, I think I just forgot to compile the code. So it is 100, which is x flash, right? And this is 1000. So just compile. Okay, now you can see the LED blinker 2 is executing multiple times when the LED blinker 1 stays as it is. Okay, the LED blinker 1 stayed high for more than 1 millisecond, for than 1 second, and only after that 1 second the LED blinker 1 becomes low. Okay, the LED 1 pin becomes low. During that time the LED blinker 2 is constantly executing. It is turning on and off multiple times while the LED 1 remains the same. Okay, so this is how tasks are executed concurrently. So you know that in Arduino or in big microcontrollers we have programmed for super loop, right? A super loop executes the functions or task one by one. Okay, if any above task delays more than expected, the task which are associated with the task will be delayed, and we don't get a real time response from the embedded system, from the microcontroller, and it will lead to a catastrophe when it is using in an industrial purpose or hospitals, etc. Okay, so for the time constrained purposes, it is better to use RTOS other than super loop. Okay, so this is how two tasks executing concurrently. Okay, so in the next lecture we are going to use our UART for diving in deep into RTOS. Okay, when we use UART, the advantage is that we can directly print the values of functions, API functions, the values which the API functions returns, and we will understand how much this configure minimum stack size and how much time each task is going to take, how much heap memory each task took for their data storage. And if when we are using queues, we need to check if we create a queue, after creation we need to check if the queue is created or not. So all those purposes we need to print some values. Sometimes it may be a integer value or true or false value, or sometimes it would be the base address of the structure or queue, or base address of the task control block, etc. So from next lecture onwards we will use our UART0 of LPC2148. Okay, so I hope you all understood this program. I will see you in the next lecture. Thank you.